This video is part of my project on creating model railway traffic lights, using KiCad to create a printed circuit board to control the lights. This is the second part of the video creating the printed circuit board. In the previous video, linked above and in the description, I demonstrated creating the schematic design in Eeschema. In this video, I'll be taking that design and converting it into this printed circuit board. This PCB is based around the ATmega 328P microcontroller. This is the same microcontroller used in the Arduino UNO and similar boards. The next stage is to take these components and relate them to a physical component, because although we've said, for instance, this is a capacitor, there can be a huge difference in capacitors from big chunky electrolytic capacitors to tiny little disc capacitors. And so we need to tell it what kind of capacitor we've got, and that's done through this tool, assign PCB footprints. If we just load that, ignore that error message, that's just a library that I've deleted. So, and these are the components we've got, and you see that some it's actually worked out a type it could be. There's actually different types we could play around with, so we'll have a look at those as well when we come up to them. But for most of them, it's left us to figure out what kind of footprint it's going to have when it's on the PCB. And there's a few search criteria that or filters that we can apply. That's the number of pins, which is usually a good one to leave switched on unless you've got a particular reason not to. And then normally switch between either the schematic symbol or the library. I'll turn the library one off. So from when it's the schematic symbol, what it's saying is C1 is normally capacitor. I'll show you all the different types of capacitors you could have. If I unselect that and instead select library, then it's looking for batteries, because that's what's selected as these libraries. If I selected the through-hole capacitor, there's the capacitor ones. So and that last one is a search if you know a particular part number or something that you're looking for. I suggest usually start with this one, and it usually makes a good guess at the type of component you're wanting to do. And so the first one is a 100 nanofarad capacitor, and that's going to be a disc capacitor. So we'll scroll past. So the SMD one's surface mount, it's not one of those. So it's a through-hole technology. Actual means that the pins come out at either end if it was a cylinder. It's not one of those, it's a disc one. And then these are the size of the disc followed by the width of the disc and then the pin spacing. And arguably the most important thing is the pin spacing in most cases. Sometimes then you need to make sure you've got the diameter as well and everything. So I'm going to use, so the ones we're going to use have got 2.5mm pin spacing and a 5mm diameter disc. It doesn't matter if it's, say, the 4.7mm disc and 2.5mm spacing. Let's say the most important thing is this, but you also need to make sure that you've got enough space for your component as well. Now, don't be tempted to press OK. I do this all the time. Just hit OK, and then it closes this app and puts you back into the thing before you've finished it. It's double click to assign it over there. And you can do multiple ones at a time, so I know that all these 100 nanofarads are going to be theirs. In fact, I also know that the 22 picofarads are the same size pretty much. So I can copy the footprint association and then paste that there as well. So there's different ways you can fill this in. The 100 microfarad, however, is very different. This is going to be a electrolytic can style, and it's going to be vertically mounted. So we can scroll through here. It's not SMD, it's not actual. So it is one of these radials. The one I've got is 5mm with a 2.5mm spacing. So you can find this either by looking at your component supplier, and they'll usually list those parameters, or you could physically measure it with a ruler against your component. So I'll just select that one. Just after warning you about it, then I've done exactly what I normally do, and that's click on the wrong button. So let's go back down to that. It was an actual 5mm. No, sorry, these are horizontal. Radial 5mm, 2.5mm spacing. Double click. So the LEDs, see if I can find 8mm LED. So there's only the one. We can use that same footprint for all three. And then this is LED small. This is the tiny little SMD one, and it's the one I've got, and it's based on the spec sheet is a 1206, and it's actually castellated, but then there's also an option for hand solder. I'm going to go for the castellated one here. I think that the hand solder probably has a slightly bigger pad. But I'll go for castellated, see how it looks. And while I'm here, another thing to bear in mind is that if you're uncertain, you can actually look at the 3D drawing and see what these look like, because many of them have got a 3D image. So for instance, let's go back to that capacitor. This one is the disk capacitor, and we can look at that, and that's what disk capacitor looks like. So if you look and think you've got the right one, look at it and it's like, oh no, it's completely wrong, then you can just use that as a additional check. And we should look at the radial thing. So this is showing what the footprint will look like on the PCB, and that's what it looks like when it's soldered on. Mine are actually slightly taller than this, but it gives you a good indication that you're at least selecting the right kind of component. So the UART, this is a connector that's going to have, basically I want pin headers, and this is actually, I mean, the number of connectors it picks up is huge, so this is actually probably a good one to search for the library rather than the part. I know that there's a connector called a pin header 2.54. I've got the number of connections still selected, and that's good because that means it will only show me ones that have 5 connections, in which case there's just 4 options here. And basically, so it's not SMD, so it's choice of horizontal or vertical. I'm going to use vertical. The power, I'm wanting to use screw terminals, so let's go to these. So there's terminal blocks. I think it might be the one I've got. It's got 3.5mm spacing between the pins. So let's just have a look at these, see if one of these looks like the right one. Could be that one, but it doesn't have a 3D symbol. So let's try and find, I know there is one on here that shows what I'm hoping for, not that one. Might be easier if I add a search term 3.50 millimeters, so that only search for ones that are 3.5 millimeters. So possibly that one. That's the one. So that looks the same as the one home. Now the others probably are the same sort of footprint. They looked it, but I'm just a bit more confident when you see the picture, and I'll mention later some checks that we need to do just to make sure you have selected the right one. Now resistor, this is an interesting one as well. So if I go back to that one, there's all kinds of resistors. I know that small one is the SMD one. Realised that I've actually forgotten to label that one, so that should be a 10 kilo ohm. But basically all four of these, as far as the pin footprint is concerned, are the same type, and they're actual ones. And I've got a variety of resistors, but generally 6.3 millimeters long are the smaller, sort of fairly standard size ones. But even with 6.3, you'll see there's different spacing, and the first two is because they're vertical, so that's why the spacing is a lot closer. Let's just have a look at these in the parts. You see that the resistor outline is very close to the pins. When you look at it, that's as close as you could physically get it. Now that's good in terms of saving space, but it does mean it's a very tight fit. So I'm actually going to go for one that's 10 millimeters long, and we can look at that, and you can see there's a bit of spacing between the connection and the resistor, and as you can see there's a bit more room to bend the pin, and that's the one I wanted to go for. So that's one I've selected for those. The small resistor is going to be a 1206, the same as the LED, and that's just the type of board. It's not castellated. Don't know if you get castellated resistors, but I'm going to be hand soldering these. So I want a 1206 hand solder. So there's see if you can tell. I'm not sure how easy it is to tell the difference between these. So that's the pad. I'll show the image as well. For one, if it's been soldered through a reflow oven. But if I switch it to the hand solder one, I think it just gives you a slightly bigger pad. Hard to tell really, but I think basically the pad is probably a little bit bigger, just to make it slightly easier to hand solder. So that's the one I'll be using. The 80 mega, so it automatically gave me this one. In fact, we didn't double check the diodes as well, so just check the diodes. Again, you've got these different spacing, the resistor, and it actually came up with quite a sensible one. I think that looks reasonable. So back down to here. So if we look at this one, the one it's automatically assigned, as you can see, it shows an integrated circuit soldered straight into the PCB, and that's probably something you don't really want to do. I almost always recommend having, for integrated circuits, having a socket, an integrated circuit socket, so that you can potentially remove the chip, either if you've got a problem with it, or you need to reprogram it separately, or perhaps you want to just move it into another project. I've built several of these Arduino type circuits, and if I've run out of the 18 mega chips, I'll just take one out of another circuit. So instead of going for that one, I'm going to use the socket instead. And if we just look at this, it shows you, there we go, that it's a socket that's mounted, and then you can put your chip in there and take it out. And the main thing is that it gives you a little bit extra space around the outside the socket, so that you don't try and put things too close to it. Now, the only thing I do wish, and I know there is a feature suggestion in KiCad, was that it would show you the integrated circuit as well mounted in it. It would look better when you do your 3D images at the end, but it's not an issue. It's just a very minor little annoyance. Finally, the last one is a crystal, and reading on the manufacturer's or the retailer's website, I know it's a HC4N. So there's 3 different kinds. I know it's that top one, but I'll just show you the other ones. So this one would be if you've got one of these very big. So HC4N is the size of the base of it, and this one is giving you space to lay it horizontally if you don't have the height. But mine isn't that tall anyway. This one shows you the same. Vertically a really tall one, but the one I've got looks like this one, which is much smaller. That's it. So that's the right one. So that's how you can just keep looking around and find the right one. Once you've done all that, then click OK, and they're all assigned. So I did notice while I was in there a couple of things that I might want to change. That wrong mode. One, I haven't changed the name of that, so that's 220 ohm SMD. I could put SMD in that if I want, but it's going to be obvious when we get onto the next stage. Well, I just noticed as well that doesn't look good. I don't think it's a problem, because the rule checker would have picked it up. I could just rewire that, make sure it looks neat. The other resistor doesn't have a value on it as well, which is this one here, and that should be 10 kilo ohm. So that's just something else that you can spot in there as well. So now we've assigned everything, everything's annotated. I'll run the rule checker again, but we've not done anything that should have broken that. So the next thing is to export a netlist. And a netlist describes all the components and their connections and how they're connected together, and that's what we're going to need when we move on to the PCB. We want it in the Pcbnew format because that's the tool we're going to use. You could use it to generate netlists for other tools as well, and just generate netlist. Now we can move on to the PCB, which we could have done. We could go back to the project page and move on to the PCB, but there is a convenient button in there as well. Starts completely blank. It hasn't even copied the title over. I think there was some options for those when we were in the thing, so you can fill those in with the page settings as we did before. This is the custom Arduino circuit. You could fill in whatever details you want. But at the moment it's blank. It isn't aware of the other circuit, so we need to import the netlist. So we exported the netlist from the previous one, import it into Pcbnew. It adds all the symbols, tells you about it all, and then you just click update PCB, and then you can close that window. And there are all our components. They're literally just thrown together as close as they can squeeze them, and it's a bit of a mess. So we need to just move these around into however we want these. The interface is a bit different from the other one, from Eeschema. When you're in Eeschema, you just hover over it and press M, for instance, would allow you to move it. In here you have to actually select it, and it's a bit disjointed when you've been used to it working one way in one and then differently in another, and it's the same app, but it's one of those things we just to get on with. So I'm just going to try and range these. For instance, I want the 3 LEDs together at one side. I'm going to try and move a lot of the other circuitry over to the other side. To know the crystal gums needs to be over here, so and just pressing R to rotate if anything's facing the wrong way. I'm going to move this is the power supply. I'm going to put that down this bottom corner. And there's the capacitor that goes with it. And so that's one of the diodes. I'll carry on moving them around. The things I'll show you while we're doing this is the 3D viewer, because you can just also refer to this just to have a look and a feel as to how the circuit's starting to form. I didn't assign these different colours, so they're just all shown as red, but that's fine. It's just used as a bit of an overview. Looks like I've selected the wrong component there. Should I update that? I don't think it matters, to be honest, because it's the same thing. But let's go back to here, and you'll see actually that the component I've got selected in Pcbnew is highlighted in here, so you know what component you're editing. That should be a different one. Should have been that one. There we go. Every time if you make a change in here and you need to reflect that back in the PCB, you have to re-export the netlist. So generate the netlist again, just give it the same name. Go back to your PCB and then load the netlist and update PCB. and you can see it's just updated that one crystal. So it sort of shows how they're a little bit disjointed in that you have to use that export and import, but just as long as you're aware of it, then it just becomes sort of second nature. There we go, so that's better. Happy with all the rest of the components, look fine. Let's carry on positioning them. I'm going to move to make sure you select the whole component, whole footprint. Move that up there along with the LED. So as you can tell, these are the surface mount components. They don't show a hole through them, they're just soldered straight on top of the board. Another diode there, let's move that over here. These ones are across the supply, and really we want to try and get these as close as possible to the power supply pins, which are located each side of the processor. We can just go to the schematic just to, so I think this one, yeah, is the AREF one actually, so pin 21, the PCB, so pin 21's over here. As you can see, the wires from here go to that side, but that one, which wants to go to the diode, is at the wrong side, so just click on that and rotate it, then move it over there. So just to have a quick look at that, see how it's going to look. You can just keep jumping into now to this 3D viewer, so that looks okay. Generally you try and make a printed circuit board as small as you can. One thing I didn't put here actually is mounting holes. I'm not sure I need them for this, but it might be a useful exercise just to go through how you'd add them. So I'll quickly show that as well actually. And again, it's going back to the schematic. We're going to go back to mounting holes are a component just like any other. So just to add, and then just search for mounting holes, and you can have them with or without a connection. We'll go for without a connection for these ones. Just do 4 mounting holes. Again, remember just to, oh, we might need to, oh yeah, we need to animate these and then annotate these. So redo the annotation because we've added new components. Then assign a appropriate sized mounting hole for all of these. We go for a quite small one, M3 or M3. Go for that. Export the Netlist again. Then we can go back into the PCB and update, re-import to the Netlist. There we go, and there's our mounting holes. Let's just do these. can use shift in here to select multiple components and to move those. And you could just spend ages and ages doing this, depends how accurate you want it, how, but just, I think I'm going to leave that like that. That looks fairly reasonable. At this point it's a good idea to actually mark out the boundary of the PCB so that when we're routing the wires around we know where to do it. Sometimes you might want to do this later on. To do that we need to understand about how these layers work. So have a look through this thing on the right hand side, and this is the different layers, and you can see everything's turned on. CU is for copper, so this is the front copper layer and the back copper layer. You see these are, we'll see these when we've run the wires. Adhesion layers, paste layers. The silk layers is the writing that you see, and everything that's in turquoise will be printed usually in white on your printed circuit board as a silk screen. And you can also add silk screen on the back as well. They're the solder masks. You can put any user drawings on theirs that don't get sent. Edge cuts is the cutting of the printed circuit board. That's the bit we're going to need now. And lastly, I'll mention the front fabrication. Fabrication assembly information. So this is all the, turn them off, all the references, like the values, and this is if you're using this for fabrication, knows which ones to pick. But where I like to move a lot of these values onto the silk screen so that you can actually see what value capacitor, for instance, and resistor you're supposed to be putting in at that point. So the layer you're editing is the one with the little blue arrow, and the tick means it's showing. So what we're going to do is we're going to go to the edge cuts, and the edge cuts is going to define where the edge of the printed circuit board is. Use this polygon tool, and we just mark top left hand corner, and then if you hold control it'll give you a nice straight line, and then again control and double click that, and that's defined where our PCB will be. You can use different shapes, you can have the cuts into whatever shape you want, but this is quite common as you do a rectangle. So just before it was guessing where we wanted that line, now it actually knows. If we'd made it bigger, then it would make the printed circuit board bigger, etc. Go out of that. And then the next stage is to start wiring things up. So we've got two layers, which is quite typical. I've got a track size set of 0.25 millimeters. Again, that's quite a good default. If you've got a lot of power, then you might want to increase that. So you can add predefined sizes. You could add, say, a 0.5 millimeter for the power tracks, but I'm just going to do it all in 0.25. That's capable of carrying about 800 milliamps quite comfortably without much of a temperature rise across the board. Just notice that capacitor, do it turning round. So now we can start wiring some of these up, and that's turning round. Make sure I actually connect that. There we go. We can choose which layer we're going to start wiring upon, whether we're going to start on the top or the bottom. I'm going to start on the bottom, and I'm going to try and wire everything as much as I can on the bottom and then on some on the top. If we need to put vias, then we can do so. I'll explain that in a while. And generally I'm not going to connect the grounds because I'm going to use ground planes. I'm just going to use a ground fill to fill up the rest of the PCB, and I'm going to do that on the top and bottom layers. I've done circuits where I've done a ground on one layer and a positive voltage on another layer, but for this I'm just going to use 2 ground layers. So let's just use, so we're on the bottom layer, so all the lines will, we click on the root tracks and the lines will show as green to indicate they're on the bottom layer. And we'll just start joining some of these together. You can use your click of your mouse to try and route. It's going to try and make a fairly sensible route anyway, but if you just add some points, you can steer it where you want it to go. And for these capacitors that are smoothing capacitors, I want them really to be as close as possible to as short as possible from here. So even though there's going to be ground plane, I'm going to try and wire these pretty much directly into here. Now, as you see, that wire would have to cross this green wire. The alternative is it has to go all the way around there, but instead I can just move to the upper layer and we can run that one like that. Now this pad has to cross these, however it could also go instead through the middle of those resistors because there's no copper there. Don't. Okay, that's so this is on the top layer. This is a surface mount device, so it doesn't have a via, doesn't have a hole going through to the bottom layer, so it has to be on the top layer. So in that case, doesn't need to go through there at all. So let's do all these actually, because it's going to dictate somewhat what to do with the rest. And move back to the bottom layer. It's like that resistor's going an awful long way, so actually I'm going to move that a little bit. Just get rid of those wires. Move that. It makes more sense for it to be there. Back to the you notice that all the angles are like 45-degree angles rather than having 90-degree angles. That's becomes more important when you've got high signals, high frequency signals. It shouldn't really be a problem on here, but it makes sense to do so. Now I'm deliberately leaving these grounds because they'll get picked up by the ground plane. So I've been able to do this without any wires, and in fact with hardly any wires on the top level at all. If we did need to cross over from one layer to another, say for instance we wanted to run a wire from here somewhere and it had to cross over red and a green, then we would run it on the green layer, the bottom layer here, and then move it on a wire. And I'll just show you how you do that. I won't do it there. So if we imagine we're running a wire here, need to change the level, you'd press the V to add a wire, which you would add there, and then you change colour, change level, and that's how you'd move from one layer to another. And what a wire is a tiny little hole that gets drilled and filled up or plated to allow the signal to pass through. So I'll just get rid of that. So now we've routed it all apart from ground. So we've got 9 unrouted connections, ground, 2, 3, yeah, no. So we can put our copper fill in, and that will connect up all the grounds. So we had a filled zone, and we're going to just do the bottom layer first in ground, and this is going to create a ground plane all across the bottom layer. And I've actually got, and that's what it's going to do. It's going to fill all this green area. Is going to be ground, and that's managed to route all the other connections as well. I'm going to put one on the top layer as well. And that's going to be on ground as well. And you can't really see much once these are on, so hence there's separate buttons, you can just turn them off. Well, this one just shows an outline, that shows areas, that an outline over areas. That one's probably the best one. And there we go. So let's have a look at that, how it looks in 3D. So the last thing to do is to put any on any silk screen, and then to export it. What I do, just like we had a design check tool in the schematic, we can use the design rules checker here. This is going to check quite a few of things, whether we've got anything unconnected, and whether we meet all the requirements that's set in our parameters we don't run wires too close or anything like that. And this one's absolutely fine. So now it's just a case of the text, and particularly, so this, as I said, the grey text, which is the fabrication layer, this won't show. All the text that's going to be written on is this blue layer, so the blue silk screen layer. And see, it shows where the components are going to go and the labels for these. So let's just start off by moving some of these. I'm going to turn the fabrication layer back on. So I like to be able to see when because I'm designing these for hand soldering, what the value should be, more than I want to see the R values, for instance. But it's useful to have both on potentially. So if you move over the actual the line you wanted to move, and we can just move these. So we're going to have a bit of a challenge in fitting that in. We can either not show anything in there, or we can have it over the line, or we can have it around here. I think I'm going to go for here. It's going to be partially obscured, but I think that's alright. So remember, these aren't on the visible layer at the moment. If we right click and click on properties, or E, we can change them onto the silk screen layer. And anything that is in this turquoise colour will be printed. In fact, thinking about it, the references are smaller, and once you soldered it on, you don't need to know the values. So if we move the reference over here, you can hide that one because turn the visibility off. I think that will look alright like that. So as you can see, you can make it look quite neat, but it takes time to do so. I think it's more useful if I show you how you can actually write on the silk screen. I haven't really left myself much space here, but I can manage that. We can add some text here to tell us what these should be connected to. So there should be DTR, then transmits, and remember this is of the UART rather than and we want this on the silk screen layer. There we go, so that writing's quite big. That's set to 1.5. 1 is the normal sort of size, which is 0.8. I might need to space these a bit more if I'm doing this one. place them. Go. That's how you can add text on, and we'll probably add some text down here that says this is, should really switch to silkscreen layer there. There it comes up. This is our custom Arduino board version 1.0, and I'll put website address on there as well. And then we can go through and tidy it up as much as we want. Once that's finished, and this is a usable board, so we could do it at this stage, we need to prepare it for manufacture, and that's really just creating the appropriate files. That's done through, and the first thing is through the plot option, and whoever you're using to create your PCBs, assuming you're sending them off to be fabricated, will tell you which of these layers to turn on and off. Usually you can probably just accept the defaults. I'll look OK. Choose an output directory. You might want to create a directory, plots or PCB in my case. I'll have it relative yet, and then click plot, and it creates the Gerber files. There's quite a few different files. Well, it's just effectively a file per each layer that's ticked on, and they're what need to be sent up. There's one more file you do need to create, and that's a drill file as well, which will say where to drill holes. And normally you can just accept defaults and click generate drill file. The one I'm sending to actually asked me to merge the through holes so into a single file, so I just need to tick that on and then click the generate file, and this for mine will generate a single, whereas if you had that, it would create two drill files, one for plated and one for non-plated is what those stand for. So we've done that, and then it's ready to go. You could literally just copy those across, but it's a good idea to do some checks first. So if we go back to the main application, leave those open, you'll see there's GBR, a Gerber viewer, so we can load the Gerber viewer and we can have a look at what it's going to look like. We've had a look at it in 3D mode on there, and this is going to show you the actual files that you've created. So if you've created the wrong files or anything, then this will potentially show that. So it's all apart from the GBR job file. That's better. So this will show you, and like we had before, we had all the different layers. We've got them on here, so you can look at them in terms of, that's the green layer is the black copper layer, and there's a mask to go with that, and a paste layer, we don't need that, and then that's the front copper layer. You can just turn these on and off and look for things like any obvious mistakes, anything that's wrong. You see the silk screen. Turn the others off there, yeah, so we can see the silk screen. And then we also want to check the drill file as well, so you can load that as well. Open an Epsilon drill file. We've just got one on here. So sometimes the default would be to create two. And to look at that, use this layer and look for the drill layer. There we can see this is where all the holes are going to be drilled, these blue markings. And all that looks fine. So one last thing I suggest you do is to check that you've chosen the right components, is to go back to the PCB view and use the print option as well. And you probably don't want the copper on, but have these rest on, so you're looking for these silt layers, the margin. What we can do is print that onto your printer, so get a physical copy, make sure it's set to 1:1, and then you can actually try pushing your components through to make sure you've got the right size holes, and if they don't fit, then you know you have to go back and do that. So that's one last check that I do recommend you do before you send it off, because potentially you're sending these off. A lot of the PCB manufacturers are based in China or the Far East, and they've got up to 2 weeks delivery times after you've sent it to manufacture. So always a good idea to do as much checking as you can, and obviously the cost aspect. You don't want to be ordering a whole load of PCBs and they're not being any good. And so that's it. So we've gone through from the very start, where we started with creating the schematic. Remember, we had to annotate, mark all the unused ones, unused ports, run the design checker, assign the footprints, and then generate the netlist. And that was all done in the Eeschema. Then we went to the PCB, we imported the old tier, rearrange, add the wires, label everything, add the ground plane if that's what you wanted to do, then export as your Gerber files, and then we're ready to go. So there's quite a long process, but very rewarding when you see the actual printed circuit boards and you get them in your hand. So this has been quite a long video, and I hope it's been useful, and hopefully set you on this process of creating your own printed circuit board. This video has shown a slightly simplified printed circuit board design to make the video easy to follow. The final PCB that I designed is based around the same initial design, but has additional components, and the board is smaller. So it was more challenging and took longer to route all the tracks into the smaller PCB. I've had both manufactured, and both designs are available to download from my website. In a future video, I'll be going through the steps involved in soldering the components, programming the 18MB 328P, and future ideas for the circuit. I hope you've found this video useful. Thanks for watching, and I look forward to seeing you in a future video.